Good evening, everyone. My name is Fred Long. I'm chair of the BCS Mid Wales branch, and welcome to this evening's event, where we have, in fact, 5 speakers who I'll introduce very shortly. First of all, just some usual housekeeping. Please keep yourselves muted and your video off during the presentations. In the changeovers between the speakers, we may be able to deal with some quick questions, but please save the main questions until after the presentations, when we will have a sort of panel session with all 5 speakers. So this evening we have Doctors Fred Labrosse, Helen Miles, Colin Sarze, Patricia Shaw and Myra Wilson, all associated with robotics at Aberystwyth University, and they are going to talk about developments in robotics and vision at Aberystwyth. So over to you, Fred.
Thank you, Fred. Let me share my screen. So I'll be talking about field robotics, and this background here is a good example of the kind of work that we do. You see us here testing a tiny bit. Here is one of our robots that we've been using, and I'll talk about that in a few minutes. So I'll talk about field robotics. I am Fred Labrosse from Computer Science at Aberystwyth University. Field robotics is what I've been doing for quite a while. It doesn't necessarily mean field as in green grass or planting things. It just means robotics in the kind of the more real world, so with real applications. We like toys, and so we have quite a few of them, and we deal with all sorts of types of robots, if you want. We have wheeled robots, so like this one, which originally was a off-the-shelf Argo cat, that we then transformed into a robot by electrifying it and putting a computer in and sensors and etc. We fly devices. So the one on the bottom left is a kind of radio control type airframe that we again fitted with a autonomous controller and all that, and we can use that for a number of applications, which I'll mention later. We also obviously do drones. And more recently, although we haven't done much work on that, we are moving kind of underwater. Colin later will talk about some of the work that we've done on boats. The kind of research behind all this is autonomous navigation, which can be pre-specified. Typically, this is what we do when we use these flying devices, where we have pre-specified flying patterns. But it can also be completely autonomous in that we let the robot loose in its environment, and it drives, for example, across a field or along tracks. And the picture here was one of our tests where the robot here was driving along what looks like vaguely a track, and it's very badly marked, but actually the robot drove fairly successfully on that. I'll talk about a number of applications very, very briefly in very high level terms, and if you do have questions about any of them, I'm happy to answer questions later. So the first application is kind of survey at large scale, landscape scale. And so we've been involved in, so this was the PhD of Ben Roberts a while back. We've been involved in building 3D models and more down of large areas. So here we were surveying 160 hectares site, which involved flying one of these planes above in a regular pattern and capturing approximately 18,000 images with about 8 centimeter resolution on the ground. And we do that with a plane that costs about £500. There are commercial solutions, ready-made commercial solutions that exist, but they are like a lot of £1,000 and don't fly any better than what we produce here. And so from the images that we capture, we can reconstruct the 3D landscape that you can see here. We can also estimate what grows where, the slope of the landscape, proximity to water. We can track animals. I'll mention that a bit later on. This work was originally started by Dr. Neil Snook to survey glaciers in Greenland. And we then have used this, the team at the bottom of the slide here, use this to survey a variety of places. We also survey kind of a smaller scale, if you want, the beaches in Wales. This is work that we're doing currently with the Welsh Coastal Monitoring Centre. This is Civet's project mentioned at the bottom here. And the idea here is to develop a small, cheap, autonomous vehicle that can survey the height of beaches at regular intervals, so that the evolution of the coast can be monitored, and from which data that can then be used to build flood models and things like that. And so we started from a radio control rock crawler, and we've modified that. And so you can see a number of sensors in here. We have a Raspberry Pi in the box here, small computer. We have a GPS antenna here, high accuracy GPS. We have a 3D camera at the top here. We have water sensing to detect when we're about to enter in water, so that we can deal with that, because obviously we don't want to disappear in the sea, and a number of things like that. And we generate, or will be generating, patterns to follow based on the requirements of the WCMC to match their current procedures. We do much smaller scale surveys. So we have developed methods that use computer vision. So we have a camera that looks at the ground, and we can segment grass versus clover, or more generally broadleaf plants, which often correspond to weeds. And we have an offline method. This is a result of the offline method. So we have in green the kind of broadleaf clover in this case. In yellow, we have grass, and we have brown, which is naked soil. We also have a real-time method that runs on the Raspberry Pi at like 15 frames per second, the so-called edge computing. And so the idea is that we're currently mounting this on a rover, and with selective sprayer. And so we can detect where there's a weed, and then we spray just that weed and nothing else, which saves money, but also much more importantly is good for the environment, because we don't put a lot of nasty chemicals in the environment. Similar methods can be adapted to not just spraying, but also, for example, deciding when to reseed, or a number of operations like these. I probably should say that there are lots of commercial solutions for this already, but we are tackling the environment that is the upland environment, for which these off-the-shelf solutions don't exist. All the solutions exist for arable land, which is where there's a lot more money involved, and that's why we're working on this. I mentioned tracking of animals earlier. So we have developed a number of methods. One is using specially made tags, which were designed by Dr. Mark Neal. The idea is that you have a very simple little component that you attach to your animal, through the ear or on the collar. And this just responds to a ping, and with an ID. And so you have a plane or a drone that flies above, and it's got two devices. You've got a device so mounted far apart, so at either end of the wings or either end of a boom like that. And one of the two devices sends a ping, and the device on the ground attached to the animal responds with an ID, and the other device on the flying device receives that ping and logs it along with the current GPS coordinate of the flying platform. And then we accumulate evidence of these, of the location of the animal on the ground, and then we find the centroid of all the responses, if you want, and that gives us the location of the animal. And we get an accuracy of approximately 60 meters, which is not great, especially compared to GPS, but it's a much simpler solution, very cheap solution, and it's enough to find which field the animal is in currently. We've also, and so here's, sorry, I forgot this, we have here a typical flight pattern, which you can follow here, and each of the, you get responses from the animals on the ground, so they are here, only these here, and so you see that, for example, we get responses from ID 42 and etc., and that tells us where the animals are. We've done some visual detection of animals that's involved with a number of computer science students. So this is the kind of same view that I showed you at the beginning of the whole survey. And if you look at some close up on that, you've got images like the bottom left here, where you can clearly see that there are two animals here that are sheep. If you look at the bigger picture, they are very small, and in fact, depending on what wavelength you're looking at, they can be very difficult to spot. And there are actually lots of features on the ground that look like sheep, like big rocks, etc., especially if you consider that sheep are not always that white. A lot of them are brown. So we've had some success on that, but more work is needed still. Communication is a big problem in the Welsh Hills, and when you're in areas like I've mentioned before, often you don't have mobile phone signal at all, and there are other solutions like LoRaWAN, for example, that are possible, but they tend to be fairly expensive in power, and they need a lot of infrastructure. And so we've developed the data mule prototype. So the idea is that we capture data in the field from animals or ground sensors. So for example, microclimate sensors or cameras. And these will save the data locally. And then we have a vehicle, for example, that opportunistically is driving around. And so it could be a tractor or it could be a drone that is specifically sent for that. And when the vehicle, the mule, the data mule, is in range of these local devices, then the data is offloaded from the local device into the data mule, which then brings the information back to the farm. And we've experimented with several stages, in particular a project funded by Caerphilly County Council. We had animals that were going to a trough for feeding. And so we had a base station near a trough, and the data was being downloaded by the base station on the trough. And then the tractor would pass by and get the data from the trough. So we kind of have a two-stage propagation of the data here. We've done a lot of work on navigation, autonomous navigation, and specifically track driving. So it's kind of the autonomous car, but instead of driving on the motorway, you're driving on the tracks that in the hills that are very often very badly defined or can change dramatically. I have a picture here on the left, taken during one of our tests at the location of the original picture I showed you. And you can see that the camera was covered in rain, and the track, you probably can guess, is extremely muddy here. And so we can detect these roads and then follow them, even if they're very badly defined. The assumptions are that the road is different from the non-road, from its surroundings, in color and in height. At the beginning, we were only doing color. So the picture on the left here is purely based on color. But we've had some examples where actually the road was yellow or the track was yellow, and then it was in the middle of dead bracken, which was also yellow. And so color wasn't enough. And so we're now also using height, which we get from a 3D camera. And we have an example here where we have a lot of these detectors that are stacked on top of each other, and each of them tells us where it thinks the road is. And then we fit a circle to their position, and that guides the robot to drive along. And with this, we can drive at, well, we've never driven at 20 kilometers per hour, but we think that we can do it. We have the processing power to do it. And finally, kind of very different from field, as in green fields, we're doing some work, and Helen will talk about some of that later, but we're doing some work with the Exomars mission for the Exomars mission. And in this case specifically, we've worked on the Mars terrain simulator, which is a physical hardware simulator of the surface of Mars. And so the idea is that you have a big kind of sand pit, if you want, roughly 20 meters by 20 meters. And with a terrain that you can modify and shape to the shape that you need. And we specifically, what we did was produce all the camera systems that allow us to build, reconstruct the shape of the landscape, but also track the rover, which you can see here. So here, this is the ground terrain model. So it's a replica of the actual rover that will fly to Mars, hopefully next year. And so one of the systems tracks this rover in real time in the facility. And then we have kind of traditional CCTV cameras positioned at each of the corners. You can just about see one here to record the activities. And we produce all the software to drive on this and to assist with a variety of tasks, one of them being the reshaping of the landscape. And so the idea is that the vehicle, using its camera system, creates a 3D landscape of what's around it, a 3D shape of what's around it. And then we replicate this in the Mars terrain simulator facility. And so this was indirectly funded by the European Space Agency and in collaboration with a number of companies, Thales and Alenia Space Italy and Altec in Italy. So this was a very quick introduction to a number of projects, and you'll hear more from my colleagues later on. As I said, if you have any question, I'm happy to answer questions now if they're very brief, or later on. Thank you.
Any quick questions for Fred? You can either unmute or put something in the chat if you want.
I have a raised hand from David Jones.
Oh.
Hi there. Thank you for the presentation. So a few years back, I was looking at doing a PhD in off-road robotics, navigation, path planning.
Mm-hmm.
So how good are the robots? When you had to do the picture of the robot following the road, the track on it through the field, how good are they when you take them off the track and just let them roam free? Are they able to kind of
how good in terms of capability, as in driving off-road?
Yeah.
Extremely good. I mean, the Argo easily, in fact, so there's another, the one that we've mostly used for the road driving is a four-wheel drive robot which has Land Rover wheels. It's electric, four-wheel drive, four-wheel steering. It's easily climbing 45 degree slopes. The Argo is also very happy at 45 degrees. And we have yet to find terrain that we can't traverse.
That's cool. Is that mainly a mechanical solution, or is there software going on?
Yeah, well, it's both. I think it's mechanical and it's also software. In particular, the four-wheel drive one, there's a motor per wheel, and each wheel is controlled at the right speed for the right vehicle speed and turning. And so you have essentially the wheel spin is controlled by software, if you want.
Yeah, cool. Thank you.
Okay, yeah, thank you, Fred. So
okay.
Next is Helen.
Thanks, Fred. Fred on Fred. Let me just get my screen. There we go. Okay, so it's handy that Fred finished with the Exomars there, because here I want to talk about something quite specific in the sort of Exomars work that we've been involved with at the university. I should say there's a whole load of us who work on a variety of Exomars things, you know, including Fred and I, and several others, not just in comp sci, but also in physics. So it's a very kind of broad group of us, and we all sort of chip in our expertise. It's given me an opportunity actually to get involved, which sort of surprised me initially, because I'm not from a robotics background. I am a computer scientist, but I'm actually in graphics and visualization, not in robotics. So it wasn't an immediately obvious to me how I could be part of that. But what I've found is that actually being able to visualize things is incredibly important, particularly in the case of Exomars, and I'll sort of talk you through that a bit more now. Wrong window selected. There we go. Okay, so the Exomars mission is a two-part mission, and Fred showed you an image just now of one of the models of the rover. This is a simulated image of what it'll look like. There is a real rover. It has been completed, hasn't launched yet. It was supposed to have launched a couple of times already, but various issues have meant that it hasn't happened yet. It's kind of a two-part mission, so you might have heard some things about it previously. A few years ago, the Trace Gas Orbiter launched, so that's now going around Mars waiting to transmit data back, basically. And the rover itself will be, hopefully, all going well, launching next year and landing the year afterwards. And the rover, I mean, the whole thing is a huge collaborative mission. There's a lot of different people involved. I am very specifically going to talk about one instrument, which is PanCam, the panoramic camera. And that is right at the very top of the rover. I've got a zoomed in photo in a mo, but it's this white box at the very top. It's one instrument, but it's actually got 3 cameras in it. And it's known kind of by the team as the science eyes of the rover. And the reason for this is that it's essentially looking around to spot where they want to go in terms of science targets. So as the rover will hopefully all go well, land on Mars, it'll look around, use photos to actually guide it towards the things that it wants to inspect. Now, the big black box on the front, on the lower front part of the rover there, is actually a drill, and that can turn and actually collect samples from 2 meters under the ground, bring them up and analyze them in the laboratory, which is inside of it. So it's got all of these instruments inside to do molecular analysis on it. So there's a lot of different things that go into this and a lot of different bits of expertise. But like I say, we're focusing specifically on the PanCam instrument. So this is PanCam, and we have 3 different cameras on it, as I said. So I've actually put white circles around them so that you can see where they are, because it might not be the most obvious thing to you. At either end, we've got 2 small cameras, the wide angle cameras, called the left and right whack, wide angle cameras. And then we have the larger one, which is slightly off-centered, is the high resolution camera HRC. Now, there are 3 other things in that picture which look like cameras and are related. So I will just point those out before we move on. We're in the very middle, then there's a pair of cameras on a little white box. They're actually navigational cameras. So there are 2 extra cameras next to PanCam, but PanCam is technically the thing behind. The gold box underneath is an infrared spectrometer, and I'm not a physicist, so I won't try and explain that to you, but essentially it's kind of like, it does act a little bit like a single pixel camera sensor, okay? So we've got a whole load of imaging sensors that are at the top of the mast. And some colleagues in physics have been involved now for a while, and in fact, Fred's been working on some of this longer than I have as well, in basically working on the PanCam instrument and working out how we can make the most out of it, essentially. So the PanCam team is just that team for that one instrument is huge, and there are lots of people from different companies and universities working on it. It's being led by UCL, but here in Aber we actually have quite a big part in that we are essentially providing the tools that will allow us to validate the images, which is quite important. So one thing that I think is really, really interesting, and I didn't realize until I started to work on space missions, is that a lot of this stuff is kind of very separated. And I think that's not going to be so true for places like NASA, where they have much more kind of in-house stuff. But because this is such a widely distributed mission, lots of things can change, and lots of things kind of need to join up. And the interesting thing about Exomars, I think, is that that doesn't always necessarily happen without extra things being put in little wedges being put in place. So when I started talking to people about what Exomars was doing, it became clear pretty quickly that although they were working on a camera system, they hadn't actually checked what it could see, which seems a little bit strange for a camera. But hey, you know, they weren't worried about that at that point. They were focused on building the instrument. So that's okay. So I spotted a opportunity to come in and help. And with my graphics and visualization background, although I'm not a roboticist, I have the tools that can help solve this problem. And it's been really, really interesting to work on this. So there are several different bits of motivation for this bit of work. Aside from the obvious, actually knowing what the cameras can see, it's also about understanding what the cameras can see. And they might initially sound like the same thing, but actually it's about knowing what we can and can't see in terms of limitations, but also what we could in theory see given the right conditions. So some of it is about sort of then going into planning operations and working out how you can use the instrument. This is all the kind of thing that you would normally, try out once you've got the piece of kit ready. You'd basically learn how to use it. You know, if you were buying a new digital camera, you'd get it out of the box, you'd work out how it worked, you'd try all the switches and everything, and then you'd try taking some photos and get used to it. Unfortunately, this camera is very expensive, understandably, because it's a piece of space instrumentation, and it's taken a long time to develop, which it means that actually they don't have the chance to try it out before it gets sent to Mars properly. They can take a few pictures, but they haven't got the opportunity to really get to know it. And this is basically the biggest piece of motivation for helping them work that out. And as a bonus, actually, it really helps us explain what the ideas of the mission are to the general public, because people tend to want to see pictures when it comes to cameras. So graphics allows us to simulate things. And when I'm talking about simulating things, I am talking about simulating things as accurately as graphics will allow us. And some of that borrows from the laws of physics. So if you are familiar with computer graphics at all, this kind of thing should look very familiar. But if you're not, what we can do with graphics is we can actually take 3D models of things. In this case, we started with the actual computer-aided design model of the rover. We're able to allocate essentially cameras to the point where the cameras would actually be on the real rover. And we're able to simulate the different properties of the cameras so that they actually act in the same way that the real cameras would do. We're then able to set up particular lighting conditions. We can say where the sun is, what kind of materials are on the rover, how they react to light. And all of this, bringing it together, allows us to actually create images that simulate what the rover will be able to see. So in this image, what I've actually got here is at the top, we've got an image of the CAD model of the rover. And at the very top, you can see PanCam, and it's actually pointed in a slightly different direction. So to use PanCam, they have to select a pan and tilt angle, and the camera system, the entire camera system on the top of the mast will turn left and right to pan, and then it can turn forward and backwards to tilt. And using that, it can look all around itself, basically. So it can do sort of 360 degrees around itself. But obviously, there are still limitations to this. And below that, then, we have 3 images, which are actually showing what the cameras themselves would see when pointed at this colourful patch here, which is the calibration target. I mentioned before that we are making sure that the images are accurate. That's how we do it. we know the exact colours of those patches, and we're able to process all the images based on the data that we collect from these images, okay? Now, I started simulating some of these just to kind of help out, so people could understand what would go on there. And we realised pretty quick that actually, because of some changes that had been made to the height of the mast, things weren't quite where they were expected to be anymore in terms of the viewpoints. Coupled with the fact that around the very, very edges of each image, you have less reliable data. What we found is that you need to be really, really careful about where you point your camera when you want to collect data. So if we wanted to collect images of the calibration target, like we do here, if we make it so that the high resolution camera, that's the one in the middle, has a really good shot of the calibration target, then the right-hand whack will have a really good shot because, again, it's right in the middle, just a bit smaller. But then the left wide-angle camera, it's only just on the very, very edge of the field of view. And that is exactly the kind of thing that we need to know when planning how to use the camera system. So once you've set up the camera, you essentially run these simulations and you produce images. It's called rendering. And this is exactly the same process that you would use to create films like, you know, sort of Disney Pixar animated films, exactly the same kind of thing. So it's, you know, this is very, very easy to do. And a lot of it is just about knowing how to do this properly, essentially, and knowing what the different things that you can use are for that. And it allows you to then turn images sort of, you know, on the right hand side, we've got the 3D model of the rover there. You can actually create these images like on the left where the lighting has been simulated and we've got a kind of Mars-like surfaces and representative materials, as I was saying before. And you can actually see the kinds of things that you will really see, hopefully, when the rover lands. So I've been using this to help with some experiments, basically. And I mentioned the calibration target one already, so it's the same picture here. But that sort of opened doors for us to practice other sequences. So learning how to do things like checking where there's a small mirror that sits on the front of the rover, the rover inspection mirror. And it allows us to actually see what it's like when we want to look at that mirror. What can we actually see? We also want to look at the drill because we have an opportunity to take pictures of the samples that come out of the drill before they get taken into the laboratory. It allows us, it has allowed us to do things like developing how we're going to actually resolve certain problems. Like, for example, with the calibration target there, one of the things we need to do is we need to actually take samples of the pixels in the image and get the average color, basically. And being able to control everything about this environment means that we can set things up so they're very, very easy to work this kind of thing out. So we can do counting pixels, we can work out how to process images, we can simulate all kinds of different possibilities, and I've got some examples to show you now. So here we go. On the top here, we've got the left and right wax, and in the middle the HRC image, and that's the calibration target. And that's what it should look like when we image it, hopefully. And below, we have the same set of images for the rover inspection mirror. And the rover inspection mirror is quite small, even when you see it in HRC. So this image in the lower middle there is actually the reflection of the rover. But it turned out that actually it's a lot smaller than we thought it would be in terms of image. So we're actually starting to think about how we might be able to use certain things like super resolution to maybe give us more detailed images. In the right whack, we can just about see it in the middle there, but it's tiny. Left whack, we can't see it at all. Similar situation then with looking at the drill and the core samples that it brings up. And this brought up a really, really interesting problem. And that is that in the middle here, you can see we have two images of the sample drawer. And there's a little grey kind of cylinder that represents the sample that it will pull up from 2 meters under the ground. And in both, you know, when we actually bring the drill up to pop the sample in the drawer, it slightly covers it when it's initially dropping it in. The drill doesn't move very fast. and the sample needs to get taken into the laboratory really quickly so that it's not exposed to the sun for too long, because that will destroy some of the things that it's looking for, essentially. But because the drill is slightly in the way, it means that it's not very easy to image. Because the drill takes so long to move out of the way, it means that we actually need to really basically take that sample in before we have fully moved it out of the way, which means that we're not going to have many opportunities, or any possibly, to take photos with the left wide angle camera. And that might not seem like a problem initially, but actually they've got different properties, so they can see slightly different things. And that means that the left wide angle camera is never really going to get the opportunity that it should really have had. And that's just one of those things where, you know, the too many different teams making too many different parts, and at some point it's become a bit disjointed, unfortunately. We've also done things like looking at focusing on things, and this is what I'm saying about being able to fully control an environment. So what I'd set up here was a box with very, very precise measurements, and you can check what you can see with certain types of, or certain focus distances and things like that. And there's all kinds of things that you can do, these slightly weird kind of laboratory tests which are in this simulated environment, which are just things you couldn't do in real life, and it's proving to be really, really useful. Strangely, it doesn't seem to be a thing which is normally done, so I'm hoping that people will learn from this. So just to wrap up with that, then, that's a very, very specific example, because, as I say, my background isn't robotics really, it's graphics and visualization, and this is ongoing work because you know, there is actually still plenty to do before the rover lands, and we've got a lot of things that we still need to work out, and a lot of things that we want to try and learn how to do as best we can before we're there, basically, to make the most of the time when we're there. So they are kind of pretty pictures, but actually they are accurately modelled as well. So they're not just made to look good, they are actually giving you information which is useful. We're taking into account lighting, atmospheric effects. I'm hoping at some point to start looking at what happens when you introduce lots of dust into the environment, how that might affect things. The cameras are based on real cameras, and you can use them in the same way as you would with the real cameras, but we have this ability to actually push things beyond the boundaries of reality, which sounds really cool. So that's what I have been up to in the last few years and will be doing for a while. Thank you very much.
Thank you, Helen. Any quick questions, Helen, while we change over? So next speaker is Colin.
Right, is my screen share showing up?
Yeah, it looks fine to me.
Good, thank you. So I'm Colin Sersey, and I'm going to talk about some of the research we've done with sailing robots. So these pictures here are two of our robots. We've built many, many others though. So just a quick outline to cover. I'll sort of have a quick look at why we're doing this and what we're trying to achieve with it. Just some of the many challenges that are involved, and then a bit of a look at some of the work we've undertaken here in Aberystwyth. So firstly, very simple, is, you know, what is a sailing robot? And it's a boat that can basically sail itself. So it needs to be able to steer by moving its rudder and to hold a given course. Then the second layer of behavior is to make it sail to predefined GPS waypoint, or to perform some other kind of, you know, spatially aware task where you are sailing a course that may be specified by some other mission parameters, such as circle around this area, or, you know, try and follow the gradient of pollutant or something that you might be sensing in the water, or try and search out certain types of targets if you're looking maybe for certain marine animals. And finally, you need to pay attention to the wind direction and automatically set up your sails to make you move forward appropriately. In this talk, I'm limiting myself to things that are actually powered by the wind and sails. We have done a bit of work as well with motorized vessels, and I'll talk about why we've kind of favored sailing things a bit later. So why do we want to do this? The main driver for me has always been the idea that we should use this for oceanographic sensing. that we can put out these robots in the sea with things that will sense temperature or salinity, acidity, dissolved carbon dioxide, pollutants, or maybe we take it a step further and put hydrophones in them and listen for fish and other marine life. We can also obtain weather data such as air pressure, rainfall, wind speed, wind direction. We can also do wave heights. If we've got underwater robots that work in collaboration with us, then we might communications relay. Now, underwater robots tend to communicate acoustically with acoustic modems. Actually work very similar to dial-up modems, if any of you remember those, by sending sound through the water. And if you then want to run these anywhere where you haven't got a support vessel around, you could then relay that via one of these boats back to a satellite or some other kind of long-range radio device. In the sort of more military and border security applications, you might use these things as sensing platforms to go and sense passing vessels that shouldn't be there or that you want to go and count. And probably the one that we've done the least work on, and is probably the most challenging, is to actually do transport with these and to transport cargoes with carbon neutral or very, very low carbon impact on what you're doing. And I think the reason that one is hard is because to be of any use, the boats need to get much bigger. All of the previous applications I mentioned, you can do with pretty small boats. But as soon as you want to do transport, you're getting up to very large scales. Everything becomes a lot more expensive, a lot more dangerous, and a lot more difficult to do. There are groups elsewhere in the world who are now starting to toy with these ideas. But most of our research has been focused on those first 4 areas, really. So why do we want to use sails and not motorize it? Well, the other thing is that we've got this essentially free energy from the wind for propulsion. And from a technical point of view, that's actually easier to capture than capturing power through a solar panel and then trying to drive a motor with that. The amount of propulsion you'll get, especially on a small boat, given a deck covered in solar panels, is less than if you stick up a sail generally and capture the wind to propel yourself. And humans have been doing this for millennia with plenty of successful designs that we can use for inspiration. There's also a reliability point of view that we probably have fewer moving parts than a motorboat does to do that. You don't need a continuously rotating propeller that's likely to get fouled up and get seaweed growing on it and barnacles. Although the sail has to move, most of the time you're going to sail the same course for hours, if not days, if you're out in the middle of the sea. One thing I've always kind of wanted to do, and we did have a very small project that looked into doing this, but unfortunately never got the follow-on funding to continue it, was a hybrid motor sailboat that you could use the motor to get yourself out of trouble and for days where there wasn't much wind, and then you could also sail around and use the sail to boost the speed. So what are some of the challenges with doing this? The sea is a tough environment and it will smash your boat around. We had one boat that went out into the Atlantic, not one of ours, fortunately, but I'll talk a bit more about why it was there. And they measured the wave heights, and the biggest wave they recorded was 12 meters. And this was during the summertime. And when we're talking about building boats of 2 or 3 meters in length, that's several times the boat length, and that will do some serious damage to you. There's also a big problem with power management is that we still need to run electronics, we need to run sensing platforms, we need to run communications, we need to run navigation, and we only have realistically solar power to do that from. And that doesn't give us much power budget to play with. So there's always been a challenge around how we do power management. And this was actually the subject of my PhD, was sort of copying inspiration from the way this is done in nature to try and basically get the boat to feast or starve and to change its behavior accordingly, depending on how much sunlight it's getting. And the other really big problem is collisions with other things in the water. And this could mean other boats, it could mean floating debris. There's plenty of containers that fall off ships or wrecks or bits of wood floating in the sea. There are animals, and some of the things like whales out there are pretty big as, if not bigger than some of our boats. And ultimately, if we really get it wrong, there's collisions with the shore. And this picture here is just one example of a boat from a French university that spent a few weeks out in the Atlantic and stopped responding to them. Luckily, they managed to find it because the fishermen picked it up a few weeks later, and there was a big hole in the back of it like this. I'm not exactly sure what caused that. I think it was probably a collision with another vessel. Their boat wasn't yellow when they set it out, and the fact that there's no yellow over it suggests that something yellow hit it. So one of the biggest challenges of all that, I think, is the traffic avoidance and recognition. And when we have human, crewed boats, there are three essential ways they look out for other things. They look out with their eyes from the bridge, and obviously that is dependent on the visibility conditions. So if it's foggy, if it's dark, you do not see as far as you would normally. And commercial ships are required to keep a watch at all times and always have someone looking out the window for what's going on. They also use radar and bounce radar waves off other things, and that gives them a pretty clear idea of the larger things, at least, that are around them, but radars can get obscured by waves, especially in bad weather. And for the last few years, all commercial shipping has been required to carry what's called an AIS transponder, which is an automatic identification system that's just a fairly simple radio beacon that transmits out where the ship is, where it's going, what direction it's going, what speed it's doing, and possibly if it's in any kind of distress. And shipping also tends to stick to fairly well-established routes, and they have a set of rules they call the collision regulations about how they should pass each other to reduce the chance of two ships hitting. Now, if we want to try and implement the robot to do all of these things, radar and AIS are relatively easy to do, but getting a robot to look and see with its own camera eyes into the sea is much harder. Often we're looking at things that are very distant. They may be obscured much of the time. And from a computational point of view, this is a complicated thing to do, which is demanding of a lot of processing power and therefore a lot of energy. And it's really only in the last few years that this has become at all feasible to do on a small boat. And the last few summers, I've had a group of students basically tagging by hand thousands of images that we've acquired over the years of views from our boats and selecting what kind of obstacles they see in them. So this is just one example here where someone has tagged up some boats in Aberystwyth Harbour for us. And what we're hoping to do is train up a sort of deep learning neural network to be able to identify some of these hazards from these pictures. What I'm finding right now is actually it's a challenge to get enough pictures, and I could really do with going and spending several months in a small boat taking more pictures and then having someone else go and tag them for me. Now, really, ever since we started this research back in the mid-2000s, we've tried to stimulate it through a series of competitions. And back in 2005, Mark Neal, who was a lecturer here and my PhD supervisor, and Yves Brière from a university in France, in Toulouse, came up with this crazy plan for the Microtransat Challenge, which was an autonomous sailing robot race across the Atlantic, inspired by another race called the Mini Transat, which is a single-handed race from Europe to Brazil. And for this, for safety reasons, we limited the length of the boats to 2.4 meters. We required that they transmit their position back to us every 6 hours. I think so far all of them have been satellite-based, but we don't actually stipulate how they do it. And when they get there, they have to hit a pre-designated target point that is 50 kilometers wide. And we've been running this properly since 2010, and we've had over 30 attempts, and one has been successful, which was a Norwegian company who build these things commercially, launched their boat from Newfoundland and sailed it to Ireland 3 years ago. Also of note, at the moment, there is a project funded by IBM for the autonomous Mayflower to celebrate the 401st now anniversary of the Mayflower crossing from the UK to America. This is a solar-powered motorboat. It's actually too big to count in the Microtransat rules, but it was launched from Plymouth only a few days ago on June 15th. And I just went and checked their Twitter page before I started this talk and found they'd actually had a mechanical failure and they're currently in the process of towing it back. Which is partly reassuring to me that it does go to show even if you're IBM with near unlimited funds, these things still happen to you and not just to universities with much smaller budgets. Realizing that transatlantic racing was really, really hard, we set up some smaller competitions as well to kind of get things going. And these have become quite good for our students to attend. We've kind of had two of these. One, the Sailboat Competition started in North America by a group of engineers, and they focused a lot more on the boat design and trying to make some very sleek, very high performance boats. And they're a bit more happy to let people do radio control for some of the events. And it's aimed at schools and universities. Around the same time in Europe, there was another organization who set up something called the World Robotics Sailing Championships with a vaguely similar set of challenges, but a focus more on autonomy and a bit more of an aim at the research side of things. But in both of these, we tend to tell people to race around a course and see how quick they can get around the course, to try and do some navigational accuracy tests where they have to sail through a quite narrow channel and stay within some markers, to try and station keep and stay in one place for a given amount of time. And in recent years, they've also both evolved a collision avoidance challenge of both detecting other boats visually and picking up any kind of radio signals they might be giving with their position and acting a bit like an AIS system. So to go on to some of the work we've done here, we spent our first few years building a few very small, simple prototypes, but then we managed to get a grant to buy a fairly decent 3.5 meter long dinghy that was converted for us by a company in France who built robots professionally. And they came up with this design based on what's called a Mini J, which is a hull designed for disabled sailors. Normally in this area where the orange hatch is, a person would be sat there facing forwards with some very simple controls that are in front of them. There's even versions where you can suck and blow on tubes that control the actuators for the sail and the rudder. So people who actually have no use of any of their limbs can still go and sail these boats. And they're very stable, very good at staying upright. If they do flip over, they will self-right almost immediately. The big change that we made to ours compared to what most of the disabled sailors use, though, is that we went for a carbon fiber wing sail instead of a traditional fabric sail, because we thought that a fabric sail would probably just flap itself to pieces fairly quickly in the kind of conditions we're expecting at sea. Right to the top of this, we have an ultrasonic wind sensor. So this uses ultrasonic pulses to detect the wind direction instead of having a rotary vane, which again tends to be more reliable over the long term. There's a couple of solar panels that enough to run a few small computers and some sensors. There's also a GPS and a compass to know where we are and what direction we're pointing in. It's got 4 sort of lead acid batteries similar to a car battery, and a couple of linear actuators that move the sail and the rudder around. And this has done a few short missions. We've never really had it out in serious ocean on its own yet, partly because we didn't ever want to lose it. It cost us over £30,000 and we put a lot of time into developing it. These are just a few pictures of this boat, mostly sailing off the coast in Aber. Then we decided we'd actually like to do a transatlantic entry and build a bit of a cheaper boat. So for this, we converted a topper Taz dinghy that we got very cheaply off eBay. This is slightly shorter, it's only 2.95 meters long, but essentially we copied all of the software we'd used on the other boat and copied it to this. We couldn't afford to make a wing sail, so we actually went with a traditional fabric sail, albeit much smaller than the one you'd normally use on a boat this size. And in 2010, we were the first group to actually attempt the Microtransat Challenge by launching from Valentia Island in Southwest Ireland. Unfortunately, after just 49 hours, the autonomous control failed. We think water got into one of the electronics boxes. One theory is we'd actually sealed it up with the expanding foam to stop anything moving inside, but the expanding foam actually continued expanding and popped the seals on it. We did have a backup tracker on it that kept tracking it for another 2 weeks and showed it completely changing direction. The Coast Guard had actually said to us they would help us recover it if it got a bit further north and call it a training operation, but it never quite got to the zone for that Coast Guard group. And unfortunately, we never recovered it. Following on from that, we realized that it took quite a lot of effort to build large boats, and it often took 2 or 3 people to get them in and out of water, which really prevented them being used a lot of the times. You had to coordinate getting 2 or 3 people ready, and you had to have a nice day, and you had to go down to the harbour with the trailer, and by the time you launched it, you'd used up half the day. So something that was much smaller and could be thrown in the back of a car and at least taken up to a lake or maybe sailed in calm seas allowed us to do a lot more research on the software side, and this is what I used for my PhD, doing the power management research. And we started off with these ones on the top picture we called MOOPs, Miniature Ocean Observation Platforms. They're just 75 centimeters long. The design we took was scaled down from a traditional Nordic folk boat, and we are not naval architects, and this didn't have the best sailing performance in the world. at one of the competitions, we met a naval architect from the US who kind of took pity on us, that he liked the concept, but saw some of the problems in our hull design. And he designed us this version down below, the Maximoop, which is a 1.2 meter version inspired on the same lines, that's much better performance. He's actually launched a few of these as transatlantic attempts, and all have done fairly well until fishermen have got curious and accidentally hauled them in with their nets. Spawning from that, we've also tried to get our students interested in this, and I think 9 years ago now, we formed Aberystwyth Sailboat, which is a student robotic sailing team who've been competing in the Sailboat and WRSC competitions ever since. In that time, they've built up 3 boats, so the 2 meter long one you see in the picture here, a Maximoop like we just saw on the previous pictures, and they started but never finished a 1.5 meter one with the aim of doing a transatlantic. And each year we also try to get them to build some small boats just to get to learn the technologies. So the first generation of these were just built around plastic bottles. And 2 years ago, we started making milled polystyrene hulls for them. They got some really good boats going, and then unfortunately the pandemic stopped any further testing of those. But let's hope we can get back to that next year. So finally, if you just want to find out a bit more about this, the Microtransat Challenge webpage is microtransat.org, or there's the other competitions, roboticsailing.org for the World Robotic Sailing Championships, or see what our students are up to at abersailbot.co.uk. Did I have any questions before switching over? I see one about autonomous roll-on roller ferries in Scandinavia. Have we liaised with them? I think we did have some very brief contact with them, but nothing major yet.
Thank you, Colin. And next speaker is Patricia.
Hello, thank you. So certainly some interesting talks, and I hope you're connecting all the dots together, ready for the panel session later. I mean, I certainly do some work with Fred Newmason, who my name mentioned, on the beach surveying robots, certainly some outdoor robotics that I'm involved in. But actually most of the robotics research that I do is much more human-centric and indoor-based robotics. And so I'm very briefly going to cover a few different aspects of that research, and looking at how we can actually develop robots that are centered around humans and how humans learn. And so the first project that I'm particularly involved with is on the bio-inspired side, where the bio-inspired inspiration comes from humans. And humans are essentially one of the best learning agents that we know of, especially babies. Within the first few years of life, they learn a significant amount. They learn about how to control their bodies, they learn about the world around them and how to interact with that world. And our philosophy towards robotics is very much trying to develop a robot that can learn online in much the same way as those infants do. We actually want to physically learn. We want to have an embodied experience interacting with the world. And you may have come across a lot about deep learning recently and the wide range of applications that can do. But the downside of deep learning is very much that it requires a lot of data, a lot of time, and typically it can't be done online, especially not on a robotic platform, unless, of course, you Google with a whole room full of robot arms constantly running, repeating the same action over and over again. So the other motivation for our research, particularly when we're looking at trying to produce these models and try and learn like a child, is to try and really minimize the amount of data that we need, the learning time, the amount of experience that we need. And so we've spent a lot of time looking at how we can actually learn from a very small number of samples, how we can gain experience through interaction, and actually looking at how the brain works as well. So as part of this work, we've spent a lot of time talking to neuroscientists and to psychologists who study the brain, who study how infants learn, to really be able to produce some quite detailed models of those aspects, and to develop a system that's capable of reflecting much of that process, or as much of that process as we can at the moment, in terms of how they develop. And so the first stage of this is really learning about, when a baby's born, how to control their body. There is some learning that goes on within the womb, and we have certainly had a look at that. They're able to track lights moving outside the womb, and so they start to build up some eye and head control there, and there's a little bit of reaching and perception of left and right that's built up within the womb. But most of it, of course, is after birth. And so we typically start our modelling from the moment of birth, and within a very short period of time, newborn babies are actually able to move their eyes and control it to look towards faces, typically. It's typically the faces of the parents that are holding them. And within that process, we can actually very quickly reproduce a similar process on the eye cup. So we can actually learn how to move the eyes to be able to fixate on a target. And following that, we can then learn how to control the head. And if you look at infant development, then particularly in the first 6 to 12 months, then there's some very nice, clearly quite well-defined stages of development that they go through. These are not necessarily all limited by cognitive growth, but sometimes limited by muscle growth as well. And so actually, when they're first born, they simply don't have the neck strength to be able to lift up their neck. And one of the advantages of that is it really simplifies the problem of what you're trying to learn. So rather than trying to learn how to coordinate 6 degrees of freedom simultaneously, you can actually focus on 2 or 3. And then once you've mastered that particular skill, as you would normally, you would then go on to develop the next level of skill. And that's very much something that can be observed in infants and something that we can map over to the robot quite nicely. And doing that, we can actually build up the eye control, head control, torso control, and arm control, so the robot's actually able to coordinate what it's seeing, moving its hands to where it's looking, and being able to reach towards objects quite nicely. But that is purely looking at the motor control, linking that to the sensory perception. But that represents about the first 6 months of an infant's sensory motor development. Alongside that, though, the infant is also learning a lot of other things, and there's other aspects that shape the development of an infant, and one of those is the changes in sensory perception, particularly in terms of visual perception. And that's something that we've looked at very closely and are continuing to look at, how their vision changes and how that actually changes what they're able to perceive of the world, and how that will then impact on what they're able to learn at any point in time. So I mentioned that when they're first born, they are able to focus on faces of people quite quickly, but typically those faces actually have to be quite close, so within sort of 20 centimeters of the baby's face. And that's because they're not particularly good at depth perception at that point. They're not able to see very far, and actually everything's pretty grainy, very poor acuity, very poor field of view actually, so they're not able to see very far to the sides, but they've got a very narrow view that's literally just that short distance in front of them that they're able to focus on, which is very nice, and it's actually very useful if you want to be able to focus specifically on one thing at a time without getting distracted by all the noise that's around you. And so that can actually really help to shape your learning. So one of the other things we do is, once we've actually got that model of the motor development, we can change the perception, change the visual perception, and see how that impacts on the infant's visual development. And there's some really nice experiments we've run where, when we actually apply these limitations, it has a noticeable impact on what the child is paying attention to, and therefore how there actually changes what it's capable of learning at any point in time. So we've got a model of how the vision changes, and that actually covers the first 12 months of life, focusing on the acuity and field of view. But you can also have a look at other aspects of how visual development progresses. And so things like perception of edges and colour, leading on to shapes and movement. So very early on, infants are particularly perceptive to movement. But things like edges are not, they're not able to perceive those particularly well until much later on. So everything looks like a nice bright coloured fuzzy ball to start off with, but then as they gradually develop, then their ability to distinguish different colours and then the edges and shapes of those objects doesn't start to appear until 3 to 4 months of age. And so that's the point they can really start to demonstrate more awareness of what the objects are that they're looking at. And at that stage, we move on to the interaction with those objects. And of course, children spend a lot of time playing, and they pick up objects and they bang them around, they shake them, and they really interact with those on a very physical level to try and explore what they can do with that object, how that object behaves. And there's some lovely videos of quite young children discovering candlesticks for the first time. And they might pick up the base of the candlestick, they might pick up the candle and actually discover that it comes apart into two. And then this is really quite surprising discovery for them at that age. And they might just keep repeating that, putting the candle back into the candle holder, pulling it out just to reinforce that. But it's actually a very small number of samples compared to, say, the deep learning that would actually require many thousands of samples. And so we can simulate that playful interaction. We can reach out, pick up objects, we can move those around, try and perform different actions on them and learn what impact those have. But of course, we don't want to have to remember every single object, every single detail, and every single action that we've performed. So then we look at how we can actually start to generalize that knowledge and recognize features. And if you see similar sets of features, actually predict what's going to happen when you interact with an object. And that really reduces the amount of data that we need to store, the amount of evaluation that we need to do in order to be able to understand and learn what an object is capable of doing. Now I mentioned that we're trying to avoid large amounts of data, but actually occasionally there are times when large amounts of data are interesting. And so one of the projects I've currently got running with Hannah D, who's unfortunately not here today, is very much looking at the vision side of things and a particular aspect of infants' vision related to colour and how we perceive it. Now, if we were to look at essentially a plain coloured wall or a plain coloured object, then we would recognise that's just a single colour. But if a camera looks at that same surface, that same object, then they would actually see a whole range of different pixels or slightly different colours. And so how is it that actually children are able to recognise that? And that might well come from repeated large quantities of observations, and as they move their head around they might see that the colour changes. And so one of the experiments we were looking at is whether we could actually get a computer to learn the same thing. And so by setting up a camera that's moving around, simulating the way in which a baby moves its head around about 3 months of age, we generated a large quantity of data of lots of different scenes and have been looking at whether we can actually train a deep learning neural network to be able to recognize patches that are consistent in color, even if they vary slightly due to slight changes in lighting, potentially small shadows that can have a major impact on the ability of computer vision algorithms to be able to recognize that as a single solid object. And that's certainly work that's ongoing at the moment, but is showing some initial results coming out of it. But that's mainly the modelling learning, that infant learning that we're doing. And I should say that the work has previously been led by Professor Mark Lee, who is unfortunately retired now, and is still there in the background, but very much as a backseat, keeping up with the progress on the project. But more recently, some other projects that we're working on is actually looking at how robots can work alongside people and particularly assisting them in living. And this is a project that's mainly the work of a PhD student, Thomas Fern, and co-supervised by myself and Fred LaBrosse. And as part of this project, we're looking at how we can actually support users of wheelchairs, particularly those with perhaps the more complex disabilities where even using a powered wheelchair is quite challenging for them to be able to navigate around particularly indoor constrained environments. For example, going through doorways that can be very narrow along corridors can be quite a challenge. And current wheelchair technology might have involved some collision detections from obstacle avoidance, but it's generally quite limited in terms of the assistance that it can supply. And so one of the things that we're keen to try and develop with this is whether we can actually combine some of the autonomous navigation from robotics with this wheelchair application to see if we can actually support the user. So rather than them having to do the complex navigation themselves from one location to another, can we actually reduce the load, the mental burden, the control burden, and have it essentially do the navigation for them on a very high level. So if we want to say, take me to the kitchen, take me to the kettle, can we get the wheelchair to do that? But in order to do that, the real wheelchair, the robot in this case, has to have an understanding of its environment. It has to know where it is. It has to be able to recognize objects. And from recognizing those different objects, it's able to build up a context, a confidence in terms of where it actually is at any point in time. So for example, if we can see a fridge, an oven and a kettle, then there's a strong chance that we're actually in the kitchen at the moment. However, if we can see lots of chairs and a table, then it's much more likely that we're in a dining room. And so it's building up this confidence and actually being able to map out a home so that when you say, take me to the kettle, then not only will it know that the kettle is most likely to be in the kitchen, and that's hopefully where it last saw it, but it will also be able to plan a path and navigate that path safely, taking the user from one location to the desired location. And there's still a lot of work that we're keen to do here. So this is looking at assisted navigation, but actually combining together some of the reach work, and also of course we need to get the user in the loop as well. So how do we transfer the control between the user and the robot in order to ensure that actually the user is comfortable, because of course we don't want to be the user to feel out of control in their wheelchair. We do want it to be a shared control experience. So there's still quite a bit of work to do there going forward, but it's certainly got some nice interesting developments at the moment. And the final project that I wanted to talk to you about is about a combination of various students' work over the years, looking at how robots can actually be our companions, so living alongside robots to some extent. And not everybody is able to have pets for various different reasons, and so there is quite a range of different robotic pets that are out there at various different levels of complexity. And the one that we can see in the image here is called Miro, which stands for Biomimetic Robot, and it is modelled based on various different animals, and they do have a model, a bio-inspired model of a mammalian brain built into the robot already as part of the control system. And some of the side effects of that are that it does display certain behaviours similar to small mammals. It likes to play, it likes to have attention. It also has moods, quite strong mood swings. If any of you have met Miro, then you'll certainly know about those. And it likes to be stroked, but when it's not happy, it will actually, much like a mammal, go and find somewhere to hide. And so it has some light sensors around it that it's able to use to go and find somewhere dark to hide. But one of the things we've been doing with this robot is actually looking at how we can develop that to not just be a pet. I mean, as a pet, we can develop its ability to learn new tricks, to have some games that you can interact with its owner, much like you might do with a dog. But also actually look at some of the other benefits that a robot pet might actually offer over a normal, over a biological pet. And so some of the projects that we've been looking at is specifically looking at if the owner that has actually had an accident, they've fallen over, can we detect that? And one of the projects was looking at detecting faces if they're on the ground and then raising an alarm. But of course, it's not always possible to see the face. They may actually be lying on their face. And so are we able to recognize that there's most likely a person that's fallen down and raise that alert if they're not getting back up again? And so that can be done by mapping out the environment and detecting obstacles that aren't normally there, and potentially driving around that obstacle, observing what shape it is, and if we can, look for a face as we drive around it. But the other potential benefit of the robot, much like dogs, they will learn your routine, they will learn when you come home from work, and they will learn when meal times are and walk times are. But the robot pet here can also learn routines, but through learning routines and observing routines, if someone starts to slip from that standard routine that they follow, then it can actually be a sign of things like depression starting to kick in. Oh, and that would be my cat going over the keyboard. I do apologise. Let me get that back a moment. I do apologise. Real pets. So looking at daily routines can actually be a sign of things like depression actually starting to have an effect on our daily routines. And so whether a robot could actually be used to motivate and encourage someone to maintain their daily routine, to get exercise, to go out and about, in order to bring them back up again, or simply to remind them to take their medication, to eat, and those sorts of things. And so those are various projects that we've been looking at on the assistance side of robotics, as well as with more disabled users. And of course, those of you who are following the BCS may also know the outreach work that I do. So things like supporting robotics clubs and setting up robotics clubs, and of course Robotics Week, as we're here for this week. But that's all I've got to say for the time being. So if there are any questions before I hand over to the next person.
Thank you, Patricia. Any quick questions?
So when you were talking about the deep learning stuff, were you feeding live video feed into the neural networks? So they're learning from a live feed, was that?
So there were actually pre-recorded videos that we took. We did some pre-processing on them prior to feeding them into the network. Not a huge amount of pre-processing, mainly we were Colin mentioned the amount of time it takes to do annotations of those videos to try and tag everything, and most of the processing we did on them was to try and automate that process as much as possible to see if we could find a way of highlighting and segmenting the images to represent the consistent coloured areas. So there were all pre-recorded videos. We fed them in as video streams though, so it was getting that time sequence data as well as the individual frames.
Okay, that's really interesting, thank you.
Okay, so our next speaker is Myra.
Okay, just getting my screen up, just hang on a sec. Am I sharing the right? No, I'm not sharing the right screen, am I?
I don't think so.
No, it obviously moved. Try that one. Yeah.
That looks better, yes.
Looks better. Right, let me just get it up to slideshow. Okay, my name's Myra Wilson and I've been a lecturer in robotics and AI in the Department of Computer Science for quite a few years now. My areas of research interests is typically biologically inspired robotics, but over the years a lot of the work that I've done has been in evolutionary robotics, and that has progressed onwards into the area of networks, communication networks. So it's applying evolution to network communication, and that's really what I'm going to just quickly talk to you about today. So first of all, the problem that we're kind of trying to look at or trying to help solve is that of the scenario where people want to communicate. And I think especially here in Wales, we know quite a lot about not being able to communicate, whether that be through having no phone signal, having no access to broadband and things like that. So what the work that we looked at involved using things like these. If you see my example slide here, I've got a picture of the Zephyr from Airbus, and the work that we actually did in the later stages of this research was in collaboration with Airbus, and it looked to use their Zephyr aircraft, which are fixed wing, continual flight unmanned aerial vehicles. So this is vehicles that could stay up for weeks, months at a time, using their solar power to continually top up the power that they actually used. So people want to communicate, and that is through various mediums, whether it be through voice, video. We all know an awful lot about that in the last year. But satellite can be expensive, and it can involve delays, especially when you're trying to download quite a lot of data at one time. As we know, there are areas with no broadband, so using the internet is not possible. And we've got, and especially, kind of here in mid Wales, we actually have quite a lot of areas with no phone signal. I can vouch for that. Where I'm sitting at the moment, I would not be able to answer the phone. If I moved kind of 100 yards and went into the garden and stood on a wall at the end of the garden, then yes, I might actually have a go. So there are these areas, but there's also areas, black spots. There's areas where you might be able to get a phone signal, but depending on kind of where you're standing at that point, you might be in a shadow of a hill. There might be things that interfere with the signal you're getting. So what we were trying to do is to fly a series, a swarm of these Zephyr type vehicles in order to provide an ad hoc network, communications network, to cover people on the ground, kind of signals on the ground, trying to communicate with each other. So this is not trying specifically to communicate with the Zephyr itself, but to communicate with other users using the Zephyrs as a medium, a backbone for this network. So we wanted to find a more flexible and adaptable way of providing this. As I say, a lot of the research that I've done in the past has been involved in evolution and, as I say, with networks themselves. So the particular project that we looked at here was this idea of NeverCav. That was just our acronym for it, and it was funded by Foundation Wales, and that's universities in Wales, Welsh Government, and Airbus in South Wales. So that's where the Zephyr came into being. And what we were trying to do was design some kind of system that allows a group of, and these unmanned aerial vehicles, and these were not helicopters or anything, they were fixed wing vehicles, again, much harder in some ways to coordinate because they always have to keep moving. You can't keep them on a spot, you have to keep them moving. And they wanted to maintain an ad hoc network to support a large amount of ground-based vehicles. Now, the scenario for this kind of thing would be perhaps in an emergency. But if you stand back a little bit and think about current situation, what you could try to do with this is use these kinds of vehicles to provide a high altitude, but not satellite altitude, network where perhaps you could improve broadband in remote areas by using these kind of things as they are able to stay up for long-term usage. So the kinds of things that we were looking to do with these was to fly autonomously. So yes, you could have all these things. You could have a pilot per UAV, and you could, yes, keep them over particular areas. But again, how would you know which areas to go over? How would the pilots know these? So, kind of having some kind of autonomous system that could determine where the best position for each one of these aircraft was what we were trying to do. Now we want to maximise the coverage. And in this case, we were just looking at this kind of rescue scenario. The ground vehicles may be emergency vehicles in a rescue scenario. We wanted to manage the power consumption because, yes, although these planes are able to stay up, they do have to ration the power that they actually provide for a communications network so that they don't drain themselves and have to land. So, and they want to deal with imperfect communication. So, how do we deal with your shadows and things? Perhaps as they're banking, you might not be able to get a very good signal because of the way that the antennae are placed. So we started off looking at this as again, we've done quite a lot of stuff in the past with genetic algorithms. If you're not familiar with these, basically you build a population which kind of allows you to look at different parts of your problem. And the population that we built looked at the flight paths or the next step of flight paths in a series that would keep updating every few minutes. You would select parents, recombine and modify. So this is just part of the genetic algorithm where you just try to move things around the solution space. So you're trying to just find little bits of changes that might lead you to a better solution. You evaluate the solution and then continue through this process. Now, the evaluation is the most important point of this particular type of algorithm. And for us, the evaluation, we initially based it on what we call a packing algorithm. And that was looking at giving each UAV a maximum power that they had available for the communication, and that was taking away from all the other functions that the UAV still had to provide to keep it airborne. So we would use that and we would allocate it to the number of ground-based vehicles underneath them, depending on the closeness that they are, you can have how many you can get and what kind of power you'd need. So we used actual figures for this. So all this was based, although it's in a simulator, it was based on the real factor of the Zephyr type machines. So we got a lot of information about that, and the first work that we did really looked at what kinds of things we could do with this flight combination. We got some very successful where some of the UAVs were flying high to try and cover some of the outliers, and some were flying quite low. So we got quite a nice pattern for these kinds of things, and you could have the usage and how they flew. But we discovered that really this first graph here looks at just using that packing algorithm. And we find that if we look at what we call the good put, so that's the application communication, it would tend to tail away as the simulation progressed. And that really was because just kind of some of the UAVs were flying far too high. They wouldn't be able to keep a reliable signal. So we included a network simulator in this work. And the network simulator allowed us to provide a much more consistent good put of data through that. So a lot of this work, we've just had a paper out that's just been published in Soft Computing. So I have the reference there. This has just been a very, very quick look through the kind of the abstract ideas behind this. But there's a lot more detail in this paper here. And so what we're going to do in the future for this particular work is make more use of the network data to inform the flight path. It's all very well just looking at the power, and that gives you a lot of information, and it's helpful to help guide those UAVs in their paths and their flight paths. But using some of the network data helps you find out just how good the communication actually is. We want to work with some smaller, more lightweight UAVs, but still retaining continual flight, because I think that continuing keeping those UAVs up there and maintaining a reliable network is a most important part of this work. And again, we want to look more at the flight paths achieved, about how we can keep the UAVs from doing too much movement, but do enough movement to still try to keep as much of the underlying communication network going. Okay, so that was just a very quick run through that, and I'm happy to take any questions or email me. I put up my email on the first slide if you're interested in talking to me about this work. Thank you.
Thank you, Myra. So any quick questions for Myra before we open the panel? No? So if all 5 speakers could unmute themselves, and we can start a more general question and answer session.
So can I ask if so we do a lot of work on digital twin. Does that, as a buzzword, is that kind of entering your work at all?
I've heard it as a buzzword.
Yeah, it is.
In particular, Helen's work in particular, where you've got the virtual environment, the virtual counterpart of the physical camera, even though the camera might not exist yet. It seems quite a nice use case for it.
Mm. Yeah, absolutely. I mean, so I suppose it's tricky in the case of Exomars because there are so many different parties involved with it, essentially. But yeah, I suppose I'm kind of it's effectively doing that tiny little piece of it as a sort of digital twin in a sense. As Fred showed, there's this kind of physical twin that is going to be used on Earth to sort of simulate operations and things, but there are definitely limitations to that having these virtual environments where you can control anything in theory it just opens a lot more options up. I don't think they're making a digital twin a complete one, which it does seem like a missed opportunity in a way. I don't know, maybe that will come along for the next mission.
So some of the projects that I've mentioned will be involving digital twins or have been involving digital twins. We've been working with the MOD at some point to work on the autonomous last mile resupply. So the idea is to bring supplies to frontline troops, for example, and that relies heavily on having some digital twin that represents a lot of the aspects of the front line and well, the battlefield in general. In a more kind of nicer application, we're trying to work with a high-tech farming company to build. The idea is to build a digital, one of the ideas to build a digital twin of the farm that can be used to simulate all the operations and plan the operations and etc. to then send the vehicle to actually do the operation. And in fact, in July, we'll be starting surveying a number of tracks of a farm that is managed by the university as a first step towards building a digital twin.
That's very interesting. How do you find the farmers? Like, does the farmers get on board with the new technology, or do they?
Any farmers here tonight? Some are very open to it. Some are a lot less open to it, like everywhere.
Yeah, my sister-in-law does milking cows, and I was talking to her about something. She just rubbished the entire thing. She was just like, get somebody else to do it. Pay somebody.
Yeah, some will be very against new technologies and say, I've been doing this for years like this, why should I change? Others are much more open to it. I think, yeah, anyway, let's not get into a political discussion.
If nobody else has got another question, we're also doing a bit of domain randomization to generate data sets for image analysis. I was thinking Colin and Patricia, have you looked at that? So it kind of gets over if you're using computer animations to generate your scenes, then it gets over the problem of labeling, because you know where everything is in the scene, so you can label it all because you're creating the scene from scratch. And the work that's been published in kind of robotic arm movement seems to say that the simulated images perform comparatively with real world images. I was wondering whether you're looking at that at all.
Whenever I'm sat there annotating lots of images, that does cross my mind. But there's the complexity of building that virtual world in the first place. So I don't know that it reduces your workload, as just changes it.
Yeah, slightly more complex. Yeah.
In the world of grasping and learning for objects, robots learning to grasp objects, then there is certainly a lot of work done in simulation in order to generate the training data. Some of that is then augmented to actually be able to reduce the amount of training samples that are needed, thereby adding to the quantity of data used for the training network. So I guess in that sense, we do build environments which we can use to produce large quantities of data. For most of the research that I do, we actually want it physically in the real world, because actually there's so many things that we can't necessarily simulate that experience, that contact, that engagement, and physically responding to what you're perceiving.
Is that the embodiment stuff?
Yes.
It's interesting that I think you're right. In some applications, software simulations can help, but in other situations, software simulations are not enough. And for example, the fact that, for example, for the Exomars mission, and in fact some American missions as well, the fact that they're building a hardware simulator is kind of shows that actually, yeah, you can simulate a lot of stuff in the software, but sometimes you need that additional bit of information. And in fact, even a hardware simulator of Mars on Earth is extremely different from the actual solution. And one aspect is gravity, for example, which is tackled in interesting and different ways, depending on who you talk to.
Yeah. Okay, so the simulations aren't real enough to be useful yet.
Yeah.
Really useful.
Are there any other questions for our panel? In that case, I'd like to thank Fred, Helen, Colin, Patricia and Myra for a very interesting session explaining what's going on in robotics and vision in Aberystwyth. I'd like to thank our audience for attending this evening, and I'd just like to remind you that we have another event on Friday in association with the Aberystwyth Robotics Week. That's Dr. Ian Harris. The title doesn't sound very robotic. Does digital transformation need a dose of social responsibility? But I'm assured it is related to robotics. And then on Saturday, we have a programming contest, something rather different, but hopefully should be great fun. That's from 12 noon until 4 p.m. on Saturday, the 26th. So once again, thank you all and have a very good evening.